Okay, so I've started recording. So hi everyone, this is the last office hours that I'm taking for homework 5, and the same format. I'll go through each question conceptually. I'll not do the arithmetic or line by line per se. But if you have a doubt after a question, stop and ask me. And once we are done with all the questions, we can have one-on-one clarifications once I end the meeting. So let's get started. So the first question basically says that consider an aircraft model that is allowed to freely yaw in a wind tunnel. The model is equipped with a gyro to measure the yaw motion. Figure 1 shows the measured time history of yawing angle due to positive 5 degree step rudder deflection. Estimate yaw damping and stiffness stability derivatives for this model. Okay, so let's get started. So let me enlarge the figure a little bit. We'll need it. So first of all, you need to recall that we are only dealing with yaw here, so you can go and look into the equations of motion, the dynamical equations of motion that we developed in lecture 9. And you know that for the yawing motion, it comes out to be beta double dot minus nr beta dot plus n beta equals n delta r. So if you compare it to a second degree equation of motion or second order uh, ODE, where we discussed in your vibrations when Professor Taha asked you to review vibrations concepts, it was basically to review the second order ODEs. And if you compare, it's exactly the same format of a second order ODE times some forcing function. So we can see that by comparison of coefficients, you can see that 2 zeta omega n has to be negative nr and omega n square has to be n beta. So now it makes sense, before you go in and jump and plug in your arithmetic, you should develop a small sanity check here, which helps you avoid making mistakes. And what is that say? Sanity check? It is that n beta is typically positive, and that makes sense because omega n square will be a positive number, and we are going to compute n beta as root over omega n. So obviously, in general, we would have plus minus, but we have to take the plus solution only. And secondly, we know that frequency has to be positive and the damping ratio has to be positive, which means that NR needs to be negative. So if I'm getting an answer where NR is negative and N beta is positive, then at least that answer makes physical sense. If accidentally you get NR positive or N beta negative, you can stop, go through your calculations back and see that have you made a mistake somewhere. Now the question arises that how do we extract the stability derivatives nr and n beta which the question is asking? We have related it to omega and zeta n, but then we need to find omega and zeta n. So again, go ahead and review the concepts of second order ODE. So one of the a few things that you need to be looking out here is first of all, you need to look out for the peak time. You need to look out for the percentage overshoot and the steady state settling value. So for that, we will go ahead and look at this graph, and you'll see that obviously the steady state settling value is very clear. It's 10 degrees. So I know that beta steady state is equals to 10 degrees. Next, what do I need to find? I need to also know the time at which the peak occurs. So let's roughly sketch it out. And it doesn't have to be very exact, but obviously it doesn't can't be very off. So I would say that this is somewhere between 1 to 1.5. So I would tag this as 1.2 seconds. So this is my time of the maximum overshoot, and this is somewhere between 11 and 12. So I will call this 11.5 degrees is my maximum overshoot. Okay. So I have determined the characteristic values of a second order system. So if you go and recall, these are the important parameters which completely define the behavior or the properties of a second order system. So first of all, I found out that the steady state settling value is 10 degrees. I found out that the overshoot is 11 point percentage overshoot. So to calculate percentage overshoot, you would have to take 11.5 degrees minus beta steady state divided by beta steady state times 100%, whatever this comes out to be. And then we have seen that roughly this peak occurs at 1.2 seconds. Now, I think it becomes pretty clear. So recall that we had the relations that the percentage overshoot is given as exponential of minus pi zeta over root over 1 minus zeta square. So from the figure, you can estimate percentage overshoot, and from that you can get zeta. Similarly, um, what is the next thing that I require? I require the other unknown in my, so I have obtained zeta. The other unknown is omega n. So let's go and find out omega n. So recall that the peak, the time at which the peak overshoot happens is given as pi over omega d, where omega d is not the natural frequency, it's the driving frequency. And what's the relation between natural frequency and driving frequency? It's omega n root over 1 minus zeta square. So don't make the mistake of plugging in omega d here. This would be wrong. This is natural frequency. So go ahead, calculate zeta. You know the peak time. Go ahead and calculate omega n. So now once you have zeta and omega n from here, it's a straightforward job to get nr and n beta. Anybody who did not understand how to approach this problem, or okay, I'm gonna take that as
I have a quick question.
okay, yep.
Could you also do NV instead of
E-
N beta?
NV.
Yes.
I don't get the question. Like, how would you do NV when it's not a part of like um it's not a part of the second order system?
Oh, all right.
I mean, NV doesn't appear in the second order system. If it is a part of, like, you must have observed that after writing all the complete equations of motion, all of the dynamics, they come out to be in a second order ODE format with damping and stiffness. And then you need to determine the damping and stiffness. You need to relate them to the damping ratio and the natural frequency. And damping and natural frequency can easily be obtained by looking at the response. So you see, here we have the step response. So we have learned to characterize the second order system using their responses to different inputs. If you give them a ramp input, if you give them a step input, so they give standard outputs, and analyzing their outputs, you need to look for the steady state value, the percentage overshoot, and the time at which the maximum overshoot happens. When you have these three data, you can go forth between, you can go back and calculate the damping ratio and the angular frequency, and further go and find out what do you say, the natural frequency.
Okay, thank you.
Yeah. Anyone else before I move on to the next question? So I don't know yet. Let me check if Professor Taha has uploaded lecture 16 notes, because yesterday when I was solving the homework, I didn't see it. So let me just make sure once before I. Yes, excellent. So lecture 16 and 17 notes are now online, and you will need those to solve the second question. Not a lot, but yeah, for the values of level 1 range. So let me paste the question here. So the question says an airplane is found to have the following short period dynamics during landing, alpha dot q dot. So we have been given Never, like always, you should read it this way. So this is my what? This is my x dot or state vector derivative. This is my system matrix A. This is my state vector X. This is my input matrix B. This is my input. Okay. So ultimately, I'm looking at x dot equals AX plus BU. So you should always write this down the moment you get the question paper, because I know that linear algebra is a little bit newer to all of you and you might be a little bit confused. So immediately go ahead and label whatever you are seeing. Next, which results in a poor short period flying qualities. So basically, we don't have good enough damping and we are oscillating too much. So it's poor short period flying qualities. Design a stability augmentation system using state feedback so that the airplane will have a level 1 short period flying qualities with 5 seconds of settling time. So what are the two? So this is a good, like, this is the baby problem for an aerospace engineer when like you are getting into the world outside. Why I am saying from an engineer perspective, like this is a baby problem because the thing is that this is how requirements would be given to you. So you would be told that you have to shoot in the middle of the level 1 range. So if you go and look up lecture 16 notes, you will find that level 1 and all these level 2 flying qualities for short period dynamics are provided. And using state. So since we are looking at short period dynamics, we'll go with CAT C because that's the most commonly used phase in the flight. And for CAT C, if you go and shoot in the middle of the L1 range, it basically says that um, zeta desired is going to be 0.85. So actually the range 0.825, yeah. The range is given as a 0.35 to 1.3. So in the middle of level 1 CAT C flying capabilities, my zeta desired is 0.825. Fine. What is the next requirement? The next requirement is said that the settling time TS is going to be 5 seconds. So this is called VOC in industrial. Just a fun fact. This is called VOC or voice of customer. Those who will be taking 159 next quarter, I'll be teeing 159 as well. So in that airplane design, you will be looking at things like voice of customer, where you list down what are the requirements you want from your aircraft. And now as an aerospace engineer, it's your responsibility to come up and design that. So how can we fix this design? So they are telling that we need to fix this design or fix this aircraft using state feedback control. And what the state feedback control means that your input is going to be negative of some gain matrix times your state vector, right? So this is called the gain matrix, and this is my state vector. So now basically we have, what do you say? Can you find out, um, like if we have if we have the settling frequency, if the settling time is given to me, can I find out the desired, like what would be required for me to move forward? Can someone take a guess?
Would it be omega?
Exactly. So we all know that to manipulate a second order system, we need two things, the damping ratio and frequency. But unfortunately, the customer here has tricked us by giving us the settling time. But we are also good students. We study hard, hopefully. So we have been given the settling time is 5 seconds. And if we go out and review the notes for second order ODE, we know that the settling time is given as 4 over zeta omega n. So if my desired zeta is 0.85, I can get my omega n natural desired as well from here. Does that make sense? So once you have your omega and desired, zeta desired, which means that my equation or second order equation should look like 2 zeta desired, omega and desired, x dot plus omega and desired squared, x equals 0, or some forcing term, or basically this would be my characteristic. Actually, I should write down this would be my characteristic equation. So basically, which means that the roots of this characteristic equation should be exactly the same as what do you say? Is basically the exact roots that I'm looking for. This is my desired characteristic equation. But right now, what is the matrix I have? The matrix I have is negative 0.33, 1.0, negative 2.52, negative 0.3. Now, this equation is derived based on the zeta desired value and omega and desired value. Our airplane is not at this value right now. So if you go ahead and calculate the roots of the characteristic equation of A here, okay, delta is used to define the characteristic equation. They will not come out to be the roots of this equation. Do you agree? I mean, if it came out, then basically we would have the same natural frequency and damping ratio. So now we are being asked to shift the roots of the characteristic equation of our system matrix. And how do we do that? We do that using state feedback. So basically we go ahead and construct a gain matrix, which is given as K1, K2, and we have X equals alpha and Q. So we construct the input to be minus Kx, which is minus K1, K2, alpha, Q. So now x dot equals ax plus bu, but u is state feedback. So ax minus bku, oh sorry, bkx, which is equals a minus bkx. So now what will happen is if you multiply b with k, so b is negative 0.03 and negative 2.6, and if you multiply b with k, you will get a 4 by 4 matrix, oh sorry, 2 by 2 matrix. You subtract it from a, you will get a new matrix, and this matrix will have all numbers except there will be relations, entries k1 and k2 as well there. How will you find out k1 and k2? Now A minus BK is the desired system matrix that you are looking for. So if I go ahead and write the characteristic equation of A minus BK, it should exactly turn out to be the desired characteristic equation that I was looking for. So once I go ahead and write down the characteristic equation here, it will come out in terms of K1 and K2. And I can simply compare the coefficients of S and the constant part to get K1 and K2. So basically, what is the process of state feedback? You go ahead and look at the current roots of the system matrix. You go ahead and find out the desired roots of the system, and then you implement the state feedback. Go ahead and look at the new system matrix, which has entries in terms of K1 and K2. Go ahead and find the characteristic equation of the new system, and this new system should have the same desired roots. So I am going to write out the characteristic equation. The coefficients of the characteristic equation will contain K1 and K2. And then I have two unknowns, K1 and K2. I have two coefficients, one of the S and one of the constant part. Go ahead and compare them and you are done. You get K1 and K2.
And for this problem, do we just leave it as K1 and K2, or do we have to plug it back into the control U or delta
Oh no,
L?
you just provide me with K1 and K2. Like I just need the gain values. So has this been, I don't know, maybe due to shortage of time, but has this been discussed in class that how do you like actually implement control?
Yeah, a little bit.
Yeah, so basically, we go ahead and put in electrical amplifiers, right? So there will be a sensor which is reading the angle of attack. There will be a sensor which is reading the Q. What is Q? P is this Q is the pitch rate. So Q is going to be, so some sensor measures the pitch rate, some sensor measures the angle of attack, and then that sensor sends the data to a computer. The computer then is connected to like a servo, and the servo has an amplifier before that. So the K1 and K2 that you calculate is going to basically tell me that what kind of amplifier, what capacitor, resistor, and inductor should I use to get that value of amplification. So K is basically value of amplification. So you just go and connect the servo, and now the computer controls the aircrafts on its own. The pilot doesn't have to do anything, and the pilot thinks, oh, this aircraft has level 1 flying capabilities. When originally, without the automatic control system, it did not have level 1 flying qualities. So all that is required is you give me the values of K1 and K2. I send it to the electronics team and they design an amplifier, and then the plane becomes stable and comes out to be in the middle of the level 1 range.
Okay, thank you.
Sure. So I'll move on to the next question. So let me. Oh, so the next question says a light reconnaissance airplane has the following lateral stability derivatives during the main part of its mission. Some values are given. I've always told you not to look at the values first. At U naught 400 feet per second, use the Dutch roll approximation to design a stability augmentation system that ensures level 1 Dutch roll flying qualities. Assume IXE equals 0 and design for frequency and damping that are 25% higher than the minimum values. Comment on the results. So, how do you propose we start first of all? Which equation of motion are you going to look at if you wanted to solve this problem?
That's wrong.
Dutch roll. And what does Dutch roll involve? What's the open loop dynamics of Dutch roll? So the open loop, if you go ahead and reference the notes, the open loop dynamics of Dutch roll involves beta dot r dot equals a beta r, and the input is delta r. Okay. Now, I know that A is going to be a matrix which has entries A11, A12, A21, A22. Just hold on a second. Yep. Okay. Now, how will I find out what is A11, what is A22? I go ahead and look at the individual equations. And for example, if you go ahead and look at the individual equations, you will find out that beta dot actually comes out to be y beta, right? Yeah, is y beta over u naught times beta plus yr over u naught times r, and so on and so forth, plus the input part is y delta r over u naught times delta R. So this is A11, this is A12, and this is, so B is going to be two entries, B1 and B2, and this is B1. Similarly, you will go ahead and look at the R dot equation. So R dot equation is n beta times beta plus nr times r plus n delta r times delta delta r. So this is going to be A21, this is going to be A22, and this is going to be B2. So now I know why the values are given. Now can you guess why those values are given? You are going to go ahead and construct the system matrix. Is it clear?
Yes.
So
When do
yeah,
you divide by U0?
look at their units. Remember, go ahead and review the. So you divide by U not, like I'm not like, this is directly from your notes. Like your non-dimensionalization has to match, right? Beta dot is the derivative, time derivative of an angle. So it's per second. R dot is the time derivative of angular velocity. So it's per second square.
Okay, thank you.
And Y beta is the forced stability derivative. N beta is the moment stability derivative. So there is already an additional unit of length there. There is, so you, I mean, it's for this non-dimensionalization comes from the concept of like the lecture 13 or 14 on stability derivatives, where stability derivatives was introduced, where you were finding like CL beta, CLR. So those are the coefficients, right? But before the coefficients, you can like before dividing by half rho u square SC or SB, whatever it is, you have the force stability derivative, right? So that's what given here. I mean, we could have given you CLY beta as well, but then I would have to give you the density, the wing plan form, the chord, the span, everything. So you would have more calculation to do. Do you get what I'm saying?
Yeah, so
Yeah.
just coefficients were generally with length in them, I guess, with units.
Yeah, yeah,
We
yeah.
divided. Okay, thank you.
And the objective of putting in problem 2 and problem 3 here is realize that like analyze that you have to be good at this from a pedagogical point of view, is that in problem 2 we had already given you the system matrix and you were trying to bring the stability derivatives to a certain point. Now we have given you the stability derivatives and we are asking you to design a stability augmentation system. So now first you need to construct the system matrix based on the stability derivatives. So the fundamental concept is always going to be looking at which equations of motion should I be looking at, isolate them, look at your cheat sheet. Okay, we are dealing with Dutch roll, beta dot r dot. Where are my beta dot r dot equations? Go ahead and write down. And be assured that all of those are second order ODEs. So you can always put them in state space format. Okay. Now, you go ahead, you have determined the system matrix. So first task is done, that x dot equals ax plus bu. We have put it in this format. Perfect. What is the next task that I'm going to do? I'm going to create the characteristic equation, which is going to give me current zeta and omega n of the system. Okay. Now I have to first go and find out what are the requirements, what are the design requirements that I have been given. So to find out the design requirements, what am I being asked to look at? So I have been told that it is a light reconnaissance airplane, which means that I can consider it to be class 1. It's small and light. So this is a class 1 aircraft. And secondly, it's like reconnaissance. It means that it has to stay up for a lot of time. And let's say someone suddenly detects it, so it has to move away. So it's non-terminal, it's rapid, there is a lot of maneuvering. So it's going to be category A. So all of this, I am helping you out in the homework. I will not help you out in the exam. So you should be able well enough to grasp that how do you go and take the language of the question and put it into or deduce the exact what do you say, the exact qualities or exact flying qualities that we need to be looking for. Okay. So if you go ahead and do this, which means that, and also what am I supposed to do? Am I supposed to shoot in the middle of the range or something like that? So the question already tells me that you need to use the Dutchell approximation that ensures level 1. Assume this and design frequency and damping that are 25% higher than the minimum values. So which means that there is one small job that I'll go ahead and find out that what is the zeta minimum and what is the omega n minimum for this, and I have to shoot for 1.25%, sorry, for 1.25 times of that. That is more than 25% above the minimum values. So which means that my zeta desired is going to be 1.25 times zeta minimum for cat 1, class 1 cat 1, and omega, same for omega and desired. Omega and desired is going to be 1.25 times omega and minimum. And then it's the same story again. You basically find K by constructing the ideal matrix A minus dk, and then you use zeta desired and omega and desired to find K1 and K2. It's the same thing that we did in the last question. Ultimately, you come down to designing a stability augmentation system. Ultimately, your goal is to find K1 and K2 or all the Gale parameters. But reaching that point is also important. So is this clear to everyone? Then I will take up the last question. And also you need to provide some comments. So like what do you think? Like basically I just want you to give a short answer to what practical implementations do you see with zeta desired with the stability derivatives required to achieve zeta desired and omega and desired. So basically you have to do the back calculation as well a little bit. So you have been given six stability derivatives. And now, because of the stability augmentation system, you will see that those stability derivatives will have to change. So which four stability derivatives have to change and what is happening? Like which stability derivatives is most changed? Why does it make sense that it got changed? Stuff like that. Is that clear or are there any questions? Okay, if we don't have questions, then let's move forward. So the next question is like huge. Let me go through it step by step. Okay, so what does the problem say? The problem says that figure 2 shows the top view of an airplane with its rudder control surface. In some scenarios, the airplane and its free rudder undergo continuous oscillation during turbulence called sneaking. This behavior can be analyzed by confining the airplane's degrees of freedom to only two: the yawing motion of the airplane, represented by angle psi between the body frame and the inertial frame, and the rudder deflection delta. So the question already gives you the hint that which equations of motion you are going to be concerned with. You are going to be concerned with equations of motion for psi and delta. The scenario is akin to that when the airplane is mounted on a hinge in a wind tunnel such that all degrees of freedom are prevented except the yawing motion. So you don't need to be worried about any other equations of motion. The airplane mass is m and its moment of inertia about the zb axis passing through the center of gravity is iz. The rudder mass is mr and its moment of inertia about the hinge point is ir. The rudder hinge is located at a distance lv. I think all of these are like very clearly shown in figure 2. Is LV behind the airplane CG and XRH ahead of the rudder center of gravity as shown in figure 2. The aerodynamic loads cause a yawing moment N on the airplane about its ZB axis at the CG and a moment H about the rudder hinge. The equations of motion of the two degrees of freedom are given by IZ psi double dot equals N and IR. The aerodynamic loads can be written as this, where N beta, N delta, H beta, H delta are constants that depend on the airplane geometry. B is a reference length and U is the forward speed. So all of the required equations are already given to you. What is the first ask of the question? The first ask of the question is linearize these equations around psi 0, delta 0 and write the linearized system in a state space form. Assume no control inputs. So you are basically going to get x dot equals ax. Note that the rudder deflection zeta is state and no longer a control input. Yeah, so a good pointer. So we have two states, psi and delta here, and delta is a state here. It's not an input like in the yawing equation. So we are going to be looking at psi and delta. So um, how are we going to linearize? I mean, that's not something very difficult. You already have the equations of motion here, and you are going to linearize this equation of motion about psi and delta equals 0. You are going to make some small angle approximation, and then you will also have you also have the linearized. So these are already this can I think yeah. So these are anyways linearized. So these are already linearized. If you recall that these equations of motion that we derived are already linearized. So you can plug in the N, H, and finally get a complete equation in psi double dot only in terms of stability. So you have to ultimately, this part of the question is basically asking you to get a relation between psi dot in terms of the stability derivatives, psi dot and psi. Same for delta double dot, the thing you do with regards to linearization. Is this a confusion for everyone? For anyone, sorry.
Yeah, sorry. What do we do with the N and H equations again? Can you repeat?
So N and H, so first of all, this equation is not linearized. This is a non-linear equation. Okay. You need to linearize it. What happened? Yeah. So this is a non-linear equation. Oh, so these are non-linear equations. Why? Because of these non-linear terms. So you need to linearize them. And then N and H are given as functions of psi, psi dot, delta, delta dot, psi, psi, delta, psi, psi, so on and so forth, right? So you are going to basically think that, okay, um, how now basically if I want to get a relation between psi double dot psi, so you are going to plug in the value of N. But then you have to ask that I am linearizing this equation. So is N linearized? Obviously, that all the second order equations that we have gotten, these are already linearized. So I can simply plug them in. Does this make sense?
Yes, thank you.
And what would be the state vector? Anyone wants to take a guess? So you will get something like x dot equals ax. But what is x? Anyone wants to guess that what are the states here? If that's not clear, you will fundamentally falter over this question.
It's one of
So
them
your
R,
R,
P, Q, R, angular velocity around the z-axis.
do you see R anywhere in the equation?
Uh,
What are the two variables for which you are writing the equation?
phi and delta.
Phi double, no, psi double dot and
Oh, sorry, yeah.
delta double dot. And they are in terms of what? They are in terms of psi, delta, psi dot, delta dot. Okay. So your state vector is psi, psi dot, delta, delta dot. The order does not matter. But basically, you are writing the equations, you are writing the equation of like your x dot will come out to be psi dot, psi double dot, delta double dot. So now psi dot is equals to 1 times psi dot, delta dot is equals to 1 times delta dot. But then the linearized equations of motion will show up for the rows of psi double dot and delta double dot. This is a long question. You will have to do it very patiently. Otherwise, you'll make mistakes. Is anyone not confident that they have understood why the state vector is going to be four variables or 4 by 1 and not 2 by 1? Okay,
Yeah,
I'll
I'm
take
I'm
the
not
oh,
100% sure when
yes, someone speaking.
like
Can you be a little bit louder?
yeah, can you hear me?
Yeah,
Yeah, I guess I'm not 100% sure when you say like well yeah, why is it that it's four instead of two here?
yeah. So um, okay. So when you write down let's say I had x double dot plus 2 zeta omega x dot plus omega n square x equals 0, right? How do you convert it into state space form? You write x double dot is equals to negative 2 zeta or negative omega n square x, negative 2 zeta omega n x, right? X dot, and then you basically say that x dot is equals to x dot, obviously, and then you go ahead and write the state vector x dot x double dot is equals to minus omega n square minus 2 zeta omega n 0 1 times x dot. Do you do this?
Yeah.
This becomes your x dot, this becomes your x, and this becomes your a. Does it make sense?
Yeah, and you're just doing that for
Yeah, so now we have
what?
something called coupling. So this is for one. So even though like we had a two-dimensional state space, remember that there is one unknown variable here, x, right? And then we are taking derivatives of that. But what if I told you that there is another system where I have psi double dot plus a1 psi plus a2 delta plus a3 psi dot plus a4 delta dot equals 0. And then I had delta double dot plus B1 psi plus B2 delta plus B3 psi dot plus B4 delta dot, which means that the evolution of psi and delta is not independent, it's coupled. Psi and delta affect each other. So how can I write a state space form? So obviously psi and delta, I cannot write two different state space forms for the system. The system is coupled, it's one part. We have two unknowns, psi and delta, which means that I will go ahead and write down the next two states, next two equations as psi dot, delta dot equals delta dot. So now you go ahead and write down psi dot, psi double dot, delta double dot. And then you write a huge 4 by 4 matrix here, and then you have the states as psi dot, delta dot. Now can we fill it in? Let's see. So psi dot is obviously just 1 times psi dot, and delta dot is just 1 times delta dot. Okay. So two rows of your state space matrix are going to look like this. And then you go ahead and look at the equation. So psi double dot is equals to negative A1 psi, negative A2 delta, negative A3 psi dot, negative A4 delta dot. Then delta double dot is minus B1 psi, minus B2 delta, minus B3 psi dot, minus B4. So now you have a 4 by 4 system matrix for a 4 by 1 state. So because we have two variables whose dynamics are coupled to each other, we will have to analyze the system together. We cannot analyze them as two different linear systems. These linear systems work together. So we need to construct a state vector where all of these can be taken in account for. And since we have two independent variables, sorry, two dependent variables, their state derivative, their time derivative is going to be again two dependent variables. So there will be four elements in your state vector, and you can write a 4 by 4 system matrix. Does this clear your concept? Be completely free. I can try another explanation.
That was helpful.
Okay. So let's move. Anyone else who is still not confident about how we are going to linearize and write the state space format as given in part one?
I guess actually I have a follow-up to that.
Mm-hmm.
Relating the A1, B1, and so on in the equations to then the application of the problem. Can
Mm-hmm.
you speak to that a little bit?
Application of a I
Like
didn't get
what so apologies if this is kind of simple, but is the A1 coming from like where are we getting those values from?
so you are going to first go ahead and linearize these equations.
Okay.
When you
And then
linearize
that's
these equations, you will get equations for psi dot and delta double dot from these four equations.
okay. So those that okay, our linearization is giving us those equations, and then we are continuing the process along with what we have from the linearization.
Yep.
Okay, thank you.
That is why it says first linearize these equations, which is going to give you the equations of motion. Then you write it in the state space form. Anyone else? This is crucial. Like if you have a millimeter of doubt within you, get it clarified right now. No need to worry about whether I have the perfect words, whether it is stupid or something like that. It's better than regretting in your exam. Okay. So we move forward, and what's the next? Yeah. Assume that, okay, we have been given a lot of values. Study the stability of this system when H beta is equals to 0. So basically, all it is saying is like after you have constructed this state space form, what is this? So I'm going to just write AI BI, where I is like 1, 2, 3, 4. So by now you should have understood that when you write the equations of motion, your coefficients are going to contain these terms, n beta, n delta, and so on and so forth. Right? Do you get this part? Anyone who doesn't get this part? So what is AI and BI? AI and BI are going to be like combinations of your stability derivatives. And other system parameters. Anybody who does not get that? Okay. So now you have been given the system parameters, you have been given the values of stability derivatives. So you can go ahead and calculate the values of all this A1, A2, A3, A4, B1, B2, B3, B4. So now you have a 4 by 4 matrix for which you know each entry. And then it is telling you to plug in H beta equals 0. So if you plug in H beta equals 0, you are now going to look at the eigenvalues of the system. And once you have the A matrix, if the real part of the eigenvalue is greater than 0, it is unstable. If the real part of the eigenvalue is less than 0, it's stable. If the real part of the eigenvalue is equals to 0, it's marginally stable. If the imaginary part of the eigenvalue is non-zero, then you will have oscillations. If your imaginary part of the eigenvalue is 0, there will be no oscillations. So whether it is exponentially increasing, exponentially decreasing, or steady state, and whether it is oscillating or non-oscillating is given by the real and imaginary parts of the system. So if let's say, for example, if I put H beta equals 0 and for my one of the eigenvalues comes out to be negative, like all the eigenvalues come out to be with real part negative, what does that mean? Is the system stable or unstable? Come on, guys.
Stable for negative.
Stable. Yep. And if I have imaginary part non-zero, then am I going to say some oscillations or not?
Yes.
Yes. So, and there is an educational note if you want to get into that. And then finally, you have to show that a large negative H beta may stabilize the system. So basically, if you plug in the values of everything else and leave H beta as it is, and then compute the eigenvalues in terms of H beta. So you can calculate the eigenvalues and it will be something in terms of H beta. And then if you plug in H beta, you can show that the real part of all eigenvalues, if H beta is very negative, then the real part of all eigenvalues is going to be negative and hence is going to be positive and hence it destabilizes the system. So do you get the outline of the question? I know there is a lot of information, but at the core, the question is very simple. So if you know the concept, you will not be overwhelmed by the amount of information.
Yeah, could you just repeat what you said when with H beta if it's very negative, and then you said it
So let's do a toy problem, okay? A different illustrative problem. Let's say I had a system A equals 1 plus alpha, 2, 3, and 4 plus 3 alpha. Okay. Now I go ahead and ask you to find out the eigenvalues of the system. So you will say that the eigenvalues of the system is going to be actually, just to make my life simpler, I'll put this as 2 plus alpha and this as 3 alpha. Okay. So the eigenvalues of the system are going to be lambda minus 1 times lambda minus 4 um, minus 2 plus 2 plus alpha times 3 plus 3 alpha. Okay. Or why even include one more? Just keep it 2. So what is this going to be? Lambda square minus 5 lambda plus 4 minus 6 alpha equals 0. So lambda square minus 5 lambda minus 2 minus 6 alpha equals 0, which means lambda equals 5 plus minus root over b square is 25 minus 4ac minus 4 plus 2 plus 24 alpha whole divided by 2, which is equals to 5 plus minus root over 33 plus 24 alpha by 2. So now can I ask you the question that for what value of alpha will this system be stable? Or for what value of alpha will this system have oscillations?
If it's greater than what, 30, negative 32 over
Yeah, I mean you get
36.
the concept,
Yeah.
right? So same thing's gonna happen in the 4 by 4 system. Like in the 4 by 4 system, you will have 16 entries. Some of the entries will have H beta in them. When you go ahead and write down the characteristic equation, you will get that the four eigenvalues are dependent on the value of H beta. And then you have to comment that why, if I have a hugely negative H beta, I can see that the real part of all the eigenvalues is going to be positive, which means that the system is going to get destabilized. Does that help?
Yeah.
Perfect. Any other questions regarding the four questions in the homework? Do these questions thoroughly. They are the most important questions regarding your final. And then on Friday, I will have final review sessions. The first discussion session and the second discussion sessions are going to have different contents. So I will cover some, like I'll cover half of the topics in the first discussion session and half of the topics in the next. I will immediately post the video right after the discussion session. So if you get time over lunch to watch it, I would suggest that watch and come to the second discussion session so that you can make the best use of it. If not, then you can attend the second discussion session and go back and watch the first discussion session video. But both the discussion sessions are going to have different content. Just because we have lost one discussion session last week, so I would like to cover more content this week and finish it off. And finally, also just to make sure that you have, if you have not seen the announcement, so let me repeat it again on the video. Um, I think I have allocated. So tomorrow I'm hosting drop-in office hours from 2 to 4 p.m. Here in ELF 134B. I will be here at my desk. I might be a little late. I might be in my office by 2:15, but I'll surely be here from 2:15 to 4. And then I have a second round of office hours, drop-in office hours on Monday, 2 to 5 p.m. And then you have your finals on Tuesday, December 9th. So make sure that if you have any doubts, then please come and meet me in ELF 134B here at my desk from 2 p.m. on 2 to 5 p.m. on Monday or 2 to 4 p.m. tomorrow, Thursday. So I'm going to end the